Hi everyone, I'm Kshitij, and this is a joint work with Dr. Vasilis Gkatzelis and Dr. Shahin Jabbari at Drexel University. Our paper, Learning Augmented Robust Algorithmic Recourse, published in Transactions on Machine Learning Research, tackles the question of how to provide individuals with reliable, cost-effective recommendations for changing their outcomes from machine learning systems, even when those systems change over time. Let's start with the motivation. Machine learning models are increasingly used to make high-stake decisions, things like whether you get approved for a loan, hired for a job, or qualify for insurance. When someone receives an unfavorable outcome, say their loan application is denied, algorithmic recourse tells them, here is the minimal cost change you can make to your features, so the model flips its decision. You can see the pipeline here. A loan applicant goes through the ML model, parameterized by theta, gets denied, receives recourse advice, and after implementing those changes, gets approved. Concretely, recourse is the minimal cost change to features, so the model flips the decision. For example, it might say, increase your income by $5,000 and reduce your credit utilization by 10%. More formally, the recourse optimization problem looks like this. We minimize over all possible modified feature vectors x prime, a combination of two terms. The first, shown in orange, is the invalidity. It's a loss function measuring how far the model's output on x prime is from the desired label of 1. The second in green is the cost of modifying the individual's features from x0 to x prime, and lambda here balances these two terms. Together, these two terms form what we call the price of recourse, denoted j of x prime and theta. This is the quantity we want to minimize. Now here's the critical issue. This formulation assumes the model parameters theta remains fixed over time. But in practice, ML models are periodically retrained. For example, maybe new data comes in, the distribution shifts, regulation changes. And as shown in the timeline, when the model is deployed at version 1, recourse is issued and it's valid. But when the model gets updated to version 2, that recourse may become invalid. The individual followed the advice, made real changes to their life, but the goalpost moved. So the two existing approaches, standard recourse, which may be invalidated if the model changes, and robust recourse, introduced by Upadhyay et al. In 2021 as ROAR, hedges against worst-case model changes. And the key question here is, can we ensure that the recourse recommendation is valid even in the worst-case scenario? ROAR addresses this by turning the problem into a minimax formulation. So instead of minimizing the price against a fixed model, we now minimize over x prime, where an adversary maximizes over all possible models theta prime within an L infinity ball of radius alpha around the original model theta 0. The invalidity term now uses the adversarial model theta prime instead of the original model theta, and the cost term remains the same. This guarantees that the recourse works even under the worst-case model change within the allowed neighborhood. But here's the catch. Since robust recourse hedges against the worst case, the price of recourse can be very high, as shown by Pareto-dominates et al. In 2023. You can see the tension on this slide. Standard recourse is on one end. It's cheap but fragile. Robust recourse is on the other. It's safe but expensive. But in practice, the updated model most likely will not be the worst case. The adversarial assumption is overly pessimistic. So the question becomes, can we get the best of both worlds? Cheap when our prediction about the future model is right, and safe when it's wrong. And the answer is yes. Our approach uses the learning augmented framework, which is part of a broader movement in algorithmic design called beyond worst case analysis. The idea is straightforward. Traditional robust approaches like ROAR assume the model The adversary has full power and the designer has zero information. That's the worst case, and it leads to overly pessimistic, expensive solutions. But in reality, we usually know something about how the future will unfold. We might not know exactly, but we're not completely in the dark either. Beyond worst case analysis asks, can we exploit that partial knowledge to do better without giving up all our safety guarantees if that knowledge turns out to be wrong? So the learning augmented framework, introduced by Mitzenmacher and Vasilevitsky in 2020, formalizes this by equipping the algorithm designer with a prediction, which could come from a machine learning model, maybe domain expertise, or historical patterns, and then measuring performance along two axes. How well do you do when the prediction is right, and how badly you degrade when it's wrong? This framework has already been successfully applied to online algorithms, data structures, mechanism design, and privacy, but never before to algorithmic recourse. And that's what we do in this work. In our setting, this translates to three components. First, the prediction. The designer has a possibly unreliable prediction, theta hat, of the future model parameters. This might come from knowing that a lender plans to tighten credit standards or from observing historical retraining patterns. Second, consistency. If the prediction turns out to be accurate, we want optimal recourse cost. We shouldn't pay extra for robustness we didn't need. Third, robustness. Even if the prediction is completely wrong, arbitrarily far from the truth, we still want bounded worst case cost. The key insight is that these two goals are in tension, but the learning augmented framework gives us a principled way to navigate that tension rather than choosing one extreme or the other. So let me formalize this. We define two metrics. Robustness, shown on the left, measures the worst case price gap between our recourse x prime and the optimal robust recourse xr. It's computed as the difference in worst case prices over all adversarial models in theta alpha, and we can find xr using our robust recourse algorithm. Consistency on the right measures the price gap between our recourse and the optimal consistent recourse xc for the predicted model theta hat. And we can find xc using standard recourse applied to the prediction. Our objective, shown in the dark box, minimizes a weighted combination between beta times the robustness plus 1 minus beta times consistency. And R of x prime alpha is the price gap versus the optimal robust recourse, and C of x theta hat is the price gap between optimal consistent recourse. Beta in the interval 0 to 1 controls the trade-off. When beta equals 0, we trust the prediction fully. This is pure consistency. And when beta equals 1, we ignore the prediction entirely, and this is pure robustness. Now let me walk through our algorithm. It works in 5 steps. Step 1, linearize. So if our model is nonlinear, such as a neural network, we approximate the nonlinear model locally at x0 using Lime. This gives us a linear model we can optimize over analytically. Step 2, initialize. We set x prime to x0 and compute the worst case adversary theta prime for the current x prime. Step 3, greedy optimize. We search over all dimensions to find the dimension I and the change delta that most improves our objective. Step 4, update and adapt. We apply the change delta, and if the sign of x prime I flips, this changes the adversary's optimal response, so we update the adversary theta prime accordingly. Step 5, terminate. We stop when no dimension yields further improvement. This brings us to our main theoretical result. Theorem 3.3 in our paper states, for any generalized linear model f theta and beta in the set 0 or 1, algorithm 1 returns an optimal recourse in polynomial time. So this is notable for 2 reasons. First, the robust recourse objective is non-convex. We prove this explicitly in the paper. Second, prior gradient-based methods like ROR can only find local optima, and our algorithm finds the global optimum through its greedy coordinate-wise structure, exploiting the per-dimension decomposition of the adversary's response. And to our knowledge, this is the first optimal algorithm for any robust recourse formulation. For our experiments, we used 4 datasets. The synthetic data has 1,000 points in 2 dimensions from a Gaussian mixture. The German credit dataset has 1,000 loan applicants with 7 features. The small business dataset has about 1,100 small business application loans with 28 features. And for scalability, the ACS income dataset has 50,000 instances with over 250 features. We tested on both logistic regression and a 3-layer neural network with 50, 100, and 200 nodes. And our baselines are ROR and RBR, or robust Bayesian recourse. Now the results. This plot shows the robustness-consistency trade-off on the small business dataset with logistic regression. Each curve traces the Pareto frontier as we vary beta from 0 to 1, and different colors represent different predictions for both our algorithm and ROR. So the 3 key findings are that first, Pareto-dominates, our algorithm simultaneously achieves better robustness and better consistency than ROR for all beta values. Every one of our curves lies below and to the left of ROR's curve. Second, ROR is suboptimal. At beta equals 1, which is robustness, ROR's robustness gap can be much worse than algorithm 1, which achieves 0 robustness for linear models. And this confirms that gradient-based methods like ROR can get stuck in local optima. Third, the trade-off shape is favorable. We can gain large consistency with only a small sacrifice in robustness. This means predictions don't need to be perfect to be useful. So these results hold across all 3 datasets and both model types and all 5 predictions that we tested. Next, we study smoothness. Smoothness is basically how gracefully performance degrades as the prediction becomes less accurate. Or in other words, it measures the price gap between recourse computed with an incorrect prediction versus the correct prediction. And this plot shows smoothness versus beta for one of our datasets. So different curves correspond to predictions with different amounts of error. So we have the correct prediction, theta hat s, and perturbations of plus or minus epsilon and 2 epsilon. So we have 3 observations. At beta equals 0, where we fully trust the prediction, smoothness is 0 for the correct prediction, but spikes sharply for incorrect ones. So there's a high risk in full trust when the prediction is wrong. At beta equals 1, where we completely ignore the prediction, all curves converge to the same smoothness value. So prediction quality no longer matters. And there's interesting non-monotone behavior. So incorrect prediction can sometimes outperform the correct one at intermediate beta values. And this shows that hedging has value even when you think your prediction is good. Now the practical bottom line, cost versus validity. So this plot shows the small business dataset with logistic regression, and our algorithm is shown at multiple lambda values alongside our other baselines, ROR and RBR. So 3 key results here. First, Pareto-dominates. Our algorithm achieves higher validity at lower cost than ROR, and you can see our curve reaches near perfect validity much faster. Second, near perfect validity. Validity approaches 1 for smaller lambda values, and ROR takes much longer to climb, and RBR stays at near zero validity in this setting. Third, the algorithm scales well, as we'll see on the next slide. Here's the same cost-validity trade-off on a much larger ACS income dataset, which has 50,000 instances and over 250 features. Even at the scale, our algorithm achieves high validity, reaching near 1 for small lambda values like 0.05. Different lambda values showed different trade-offs. Smaller lambda values push for higher validity but at a higher cost, while larger lambda values keeps the cost down but with lower validity. And the key takeaway is that our approach scales linearly in both the number of instances and features. confirming practical applicability even for high-dimensional real-world datasets. So let me wrap up with our 4 main contributions. First, we initiated the study of learning augmented algorithmic recourse. This is the first work to combine predictions about model changes with robust recourse. Second, we proposed an efficient algorithm that optimizes the robustness-consistency trade-off through a single parameter beta. Third, we proved optimality for generalized linear models. This is the first optimality guarantee for any robust recourse formulation, which is significant because the problem is non-convex. And fourth, our experiments show that the algorithm empirically Pareto-dominates other baselines like ROR and RBR while running 10 to 100 times faster. Thank you for watching, and if you'd like to learn more, you can find our paper and the code on GitHub using the QR code shown here. Thank you.